Everyone. Today we're going to continue with our lessons, and I would like to mention about time and frequency scaling and how do they correlate. So first of all, let me show you if the time signal gets wider, then the frequency domain signal will get narrower. What I mean is, let me show it here. For example, we have a time domain signal like this, and then we have another time domain signal like this, and then okay, it's enough this much. And then if we do the Fourier transform, if we show the Fourier transform of these two, the Fourier transform of this one, let's say it is like this. For example, here we have, and let me show the other one also in frequency domain. And this one, since it got it widened, the frequency domain would get narrower. It has an inverse correlation. So higher bandwidth signal is needed if you are trying to switch the time component on and off faster. Here we have the switch which is turned on and off faster than this one, so we would have a higher bandwidth signal. That's why it is wider here. Okay, so if you compress in one domain, you expand in the other domain. That's the in other words, we can say it like this. Let me repeat. If you compress in one domain, you need to expand in the other domain, as it can be seen in this example. Now let's look at duality. What is duality and how we can use it in Fourier transform? Let me illustrate all this in an example. And we have an example saying that the Fourier transform of x signal in the time domain is delta function, and its Fourier transform is 1. Using the duality property, we need to work out the Fourier transform of another time domain signal, which is equal to 1. So what do we do in these situations is that we have our function, and our function is a delta function, which is an impulse going to 1, and it's 0 otherwise, as we know. And we have already said that the Fourier transform of this is 1 as well. Okay, let me write it like this. Okay, so we are asked for the Fourier transform of this signal, right? Time domain signal, which is 1. So what is duality principle? If these two are the same, then these two are correlated. It is the multiplication by 2 pi, all right? Since these two, this one and this one, are the same, then we just need to multiply this graph, this function by 2 pi, and it will give us our answer. So let me write y omega in frequency domain will be basically 2 pi. This impulse, which has an amplitude of 2 pi. So this is the end of our example. Now let us look at some other example for Fourier transform. This is a harder one. Let's look at a harder example. Xt is equal to e to the minus at squared. We want the Fourier transform of this function. We are given also that a is greater than 0. So what did we do? our first step is to check if the integral converges. The absolute value of the integral needs to converge in order for us to use our previously told formula. All right. So the first thing that we are doing is checking if our signal is converging. Okay. So what do we do here? We can just see that when we increase t, it's similar to 1 over infinity, which goes to 0. So we can say that yes, it is convergent. So we can be pretty sure that we can use our formula. So let me write. This was our formula that we used to use to calculate the Fourier transforms. Here we write this, and let me write our signals function. And now let me take into parentheses like this. So how are we going to solve this? Now let me remind you of some integral that we can make it similar in order to solve it. So if it were 1 over pi square root of pi integral from minus infinity to infinity e to the minus t squared dt equals to 1. If it were this one, we know. So if it were similar to this, we can solve it. So we need to make it somewhat similar. So what do we do in order to do so? We make a t squared plus j omega t equals 2. So let me make it similar, and we can say that this equality equals to p squared plus 2pq, right? And if we add q squared and then we subtract q squared, it changes nothing. So we can do this. And this equality equals to p plus q squared minus q squared. Now this equality will help us to make these two is similar. All right. Now let me show you how. Now we need to make them equal. Now we need to determine what is p, what is q, etc. So we said this one equals to this expression, and then similarly this one equals to this expression, and now we are just going to find out what is p, what is q. Okay, p squared, from here we can see that it's at squared, and then j omega t equals to 2pq. From here you can do all the calculations, and we will finally come up to this conclusion. P will equal to square root at, and then q will equal to omega j over 2 square root a. Okay, and then what do we have? If we need to express it in this term so that we can reach our target. So we want this expression, so we are just going to write square root at plus omega j over 2 square root a square minus the second power of square of q will give us j squared. J squared is minus 1. That's why I will just write it like this. Okay, and our final result will be like this. So let me write the let me say this equals to integral I, and I will write this integral I in our new format, which is the integral from minus infinity to plus infinity. We will have this expression over here. Let me copy this. Here we are. But we had also the minus sign. Let me just put it here. And then the t. So we can see that since these are subtracted, we can just separate these two, and we can write it like this. And since our dummy variable is t here, since our dependent value is t here and there's no t, this is a constant, right? Now we have a huge chunk of material over here, so we need to use another method in order for us to be able to compute this value. So let's just replace it with u. We are going to replace it with u. And then what do? We need to take care of this value over here. Since we are replacing it with u, we are just going to make this replacement equals to u, and then take the derivative of both sides. We would have with respect back to t. This is constant, so it goes to 0, and the coefficient of t is square root a, so we have just square root a here, and then the other part we have du over dt. So instead of t, we will just write dt equals du over square root of a. All right. So I will replace all the things that I have done. Let me write integral a equals to, from minus infinity to plus infinity, we have e to the power of minus u square e to the power of minus omega over 4a times du over the square root a. As we can see here, this is a constant, this is a constant. Let's replace them outside of the integral, and we'll just have this expression. And we have this one. And what we said earlier, we said e to the power of minus t squared dt equals to the integral of this times 1 over square root pi equals to 1. All right, when we can just put pi, we can just put pi here instead of 1, and we can say that this result is square root of pi, right? So eventually we have our result of our integral, and we can say that, let me write it here, the Fourier transform of xt equals to square root pi over a times e to the power of minus omega over 4a if a is greater than 0. And that is the end of our question. And let us shift to our next question. Let us look at this next question. And it asks us, if the Fourier transform of xt is x omega, what is the Fourier transform of yt, which is equal to x 2t minus 3? What is the Fourier transform of this? And how do we do this? We will use the properties of Fourier transform, which we have seen, such as time shifting, time scaling, etc. So let me show you. We can just write yt as x in parentheses of 2 t minus 3/2, right? Now we can do like this. We have our signal, and then our first step is doing time scaling, and then we have eventually x2t, and then instead of t we will write t minus 3/2, in other words 1.5, and this is just time shifting, right? Time shifting. Okay, and the Fourier transform of this time domain signal was x omega, and when we do time scaling, what do we do? It is written on our previous notes as well as on the graphs. We just multiply by 1 over the absolute value of the multiplied constant times x j omega over this constant. And then when we do time shifting, we are just going to multiply with e to the power of minus j omega and this value which is shifted with. And let me write it. This is our final result. And here we came to end of our lesson. Now let me remind you these properties if it was hard to follow here. Reminder, let's say. If we do time shifting, now here we have our signal and here we have our Fourier transform. If we do time shifting by x t minus t0, then our Fourier transform will be e to the power of minus j omega t0 and times the previously found Fourier transform. Okay, time and frequency scaling. Let me show that too. Time and frequency scaling. And its formula is given as such. It was just a reminder in order for us to compute this example clearly. Okay, let's move on to the next question, which asks us to compute the Fourier transform of this time domain signal, which is 1 over a plus jt. It asks us, so it is the Fourier transform. Now, I want to remind you something. Previously, in our previous videos, we have already computed the Fourier transform of an exponential, which is e to the power of negative at times ut, which is representing the unit step function, and it was a similar, in fact, the same expression. So let me just illustrate it like this. E to the power of minus at times ut, and its Fourier transform was this one. And now we are asked the Fourier transform of this. However, how we can do this without using the formula? We can just use the duality principle, right? And how do we do that? We just replace t by minus omega, and then we multiply it by 2 pi, as we already have covered this. So doing that, we do minus a, and then we write minus omega instead of t. It is our first thing what we are going to do. And then, let me also write this one. And then, what do? We are not finished yet. We are just going to multiply it by 2 pi. And then now we are done. We have calculated the Fourier transform also of this expression. Now let us move on to the next example. And the question tells us to find the Fourier transform of the graph given. So this is the graph given, and we are asked for to find the Fourier transform of this signal, time domain signal. All right, how do we do that? First of all, we need to calculate the derivative of this function. All right, now let me show you the derivative. D over dt xt, and then we have t. So what is this? Here we have the slope, which is equal to 0. And then here we do, if this is minus infinity, right? The slope is minus infinity. And the amplitude, we need to compute it, and it is 4 here, 8 here, and we have a total amplitude of minus 12. So we will have a impulse which has a magnitude of minus 12 at the point 2. And all the other values are 0. So this is our derivative function. So let me remind you of our property, Fourier transform property, and we have Fourier transform of this one is like this. And then if we were to take the derivative, the Fourier transform would be j times omega times the exact same Fourier transform. Now, we know that the derivative of this time domain function is minus 12 delta. If I was going to write like this, it would be wrong, because delta does not have the value minus 12 at 0, but it takes this value at 2. So I would be required to shift a little bit by 2 so that our graph becomes correct. And if we were going to take the Fourier transform of both sides, we would write j times omega times the Fourier transform equals minus 12. The Fourier transform of the delta function was 1. However, we just time shifted it by 2, so we are going to multiply it with e to the power of minus j omega 2. However, we need to be careful here. Are we going to make sure that we have completed all the steps? We shouldn't just leave it delta function, the Fourier of delta function as 1, because we time shifted it, and we should include also this part over here. Now, I'd like to mention about a point which is very important. Now, when we take the derivative, some of the constant of a derivative is 0. So we cannot, the DC value becomes 0, but we need to calculate it. It is also the average value, the DC value, so we can calculate the DC value, in other words, the average value from the previous graph, from the initial question graph, and from this graph, I mean. And how do we calculate DC value? Let me say. It is the average of these two portions, which is 4 plus minus 8 over 2 equals minus 2. Now let me calculate the Fourier transform of this value over here. Now we can just use our previous knowledge, and the Fourier transform of constant was the constant itself times 2 pi times delta function in frequency domain. So its Fourier transform is basically minus 4 pi delta omega. Therefore, we will have our final answer as this value over here plus this value over here. Let me write these two. And this is our final answer. Now let us look at another example. But before skipping to the next example, let me show you the reason why the Fourier transform of a constant is when we are calculating the Fourier transform of the constant, we are using this formula. Let me show you why. Now let us assume that our time domain signal is a0, which is a constant, and now we were asked to find the Fourier transform of this. Now the first condition that we will apply is to see if it is absolutely integrable. So integral minus infinity to infinity, the absolute value of this function needs to be smaller than infinity. However, is that the case? 0 dt equals, we can put a0 out of the integral as it's a constant. And now we have a hidden 1 here, so we just have t coming out. And this value is basically infinity. It's not we couldn't calculate it. It's basically infinity and not absolutely integrable signal. Therefore, we can't use the Fourier transform formula. Not absolutely integrable. We can't use the formula. Okay, and what do we do here? We just assume that the Fourier transform of this signal is a0 times delta omega. The Fourier transform of the signal, which was a0, right, at the beginning. Now, what do we do in this situation is that we have this relation xt equals 1/2 pi integral from minus infinity to infinity. We have our Fourier transform times e to the power of j omega t d omega, and we just put its place this value, and we say a0 times delta omega. And let me just rewrite this over here. And since we have a rule in delta functions, right? We have a rule and such as this. If it is like this and we have omega here, this one is equal to omega minus omega c, not as this one is takes the value 0 in all other values other than omega naught. So what do we do here? This is the same as delta omega minus 0. So we will just substitute 0 and this t over here. Sorry, I wrote it wrong here. And now, since it is a 0, it becomes 1, and integral minus infinity to infinity. We have a naught times delta omega d omega, and then we can put a naught outside of the integral as it is a constant, and let me write it here. And here, this value over here is just 1, as we already know. That's why we can say that the value A naught, the Fourier transform, is basically, let me read this. The signal, which is like this, signal, the Fourier transform is this one. So by using our multiplication property in Fourier transform, scaling property, we can say that the Fourier transform of just our constant is this one. So we eventually said what is the signal which the Fourier transform is A naught times delta omega. And then we found out that the signal which gives this Fourier transform is this. And then we had this conclusion over here. However, we just need the A omega. That's why we multiplied the signal by 2 pi, and when we multiply the signal, the Fourier transform also gets multiplied by 2 pi. Therefore, our final answer reveals how we can compute the Fourier transform of a constant.